pop quiz. At what angle do nucleophiles usually attack a carbonyl? A. About 107 degrees, B. 90 degrees, or C. 150 degrees? 5 seconds. Go. Time's up. It's A. About 107 degrees. That's the Bürgi-Dunitz angle, the preferred path into the carbonyl's lowest unoccupied molecular orbital, or LUMO, to reach the electrophilic carbon. In this video, you'll learn the big idea of nucleophilic addition, see the model that explains it, work 2 classic examples, avoid common pitfalls, and compare the reactivity of aldehydes versus ketones. Here's the core move. A nucleophile attacks the carbonyl carbon along that Bürgi-Dunitz path. Carbon goes sp2 to sp3. The pi bond shifts to oxygen to give an alkoxide, an an ion, which is then protonated to an alcohol. Think orbitals. The carbonyl's pi orbital is low enough to accept electrons. Approach along approximately 107 degrees lets the nucleophile overlap best with that orbital and minimize repulsion, guiding the reaction. Common nucleophiles include ions, like hydroxide, cyanide, and carbon ions, like Grignard or organolithium, and neutral ones, such as water, alcohols, and amines, often activated by acid. Example, cyanide addition. Cyanide attacks acetaldehyde to form a tetrahedral alkoxide. Protonation gives a cyanohydrin. Net result, a new single carbon-to-carbon bond and a hydroxyl group on the former carbonyl carbon. With aldehydes and ketones, you get addition, not substitution. There's no built-in leaving group on the carbonyl carbon. So far, we've locked in the attack angle, the tetrahedral intermediate with an ion, and how cyanide gives a cyanohydrin. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide, then jump right back into the video. Lock in what you learned and keep going. Now apply the pattern with amines. A primary amine adds to give a carbonylamine. After proton shuttling, water leaves and the lone pair reforms a bond to make an imine or Schiff base, best near mildly acidic pH approximately 4 to 5. Another staple is Grignard addition. When added to a ketone and after aqueous workup, you get a tertiary alcohol. Powerful way to build carbon-carbon bonds. Now, let's dive into reactivity trends. Aldehydes to ketones. Aldehydes are less crowded and more polarized, so carbon is more electrophilic. Aromatic aldehydes like benzaldehyde are often less reactive than aliphatic ones because resonance in the ring reduces electrophilicity at the carbonyl carbon. Some things to watch out for. Hydride delivery comes from reagents such as sodium borohydride or lithium aluminum hydride. It's not a free H- floating in solution. Imine formation can fail if the conditions are too basic or too acidic. And finally, conjugation or bulky groups can slow down the attack. Now let's follow the electrons. Add into pi orbital. Then it will form the tetrahedral intermediate, shuttle protons, and when conditions allow, eliminate to form imines or protect as acetals with alcohols under acid. In short, a nucleophile adds to the carbonyl carbon, giving a tetrahedral intermediate that then either protonates or eliminates. That's why cyanide plus acid yields a cyanohydrin. An amine under acid gives an imine via loss of water, and a Grignard, followed by workup, gives an alcohol. As for reactivity, aldehydes react faster than ketones, while aromatic carbonyls are often less electrophilic due to resonance. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.